I'd now like to talk about a reaction of a diene, and this diene has a competition process going on. Under cold conditions, we get this distribution of products where we get 80% of this one and 20% of this product. And at warm temperatures, we get 20% of this product and 80% of this product. What we're going to do is we're going to use the explanation of thermodynamics and kinetics to explain why we get these different distributions of products at different temperatures. Well, the first thing we want to do is figure out how these products get formed, because that's going to play a big role in how we explain this. So let's take a look at our first process. We know that HBr will split up into H plus and Br minus because it's acidic. The double bond will attack the H plus, and because it's going to obey Markovnikov's rule, the positive charge is going to end up on the more substituted of these two carbons from the double bond. So the positive charge always ends up on the carbons with the most carbons connected to it. So that's why it's going to end up here and not on the end. So now what's going to happen is the Br negative comes in, attacks the C plus, and we get one of our products. This one here specifically, which I will label product A. Alright, let's see how we get the other product. Alright, same situation again, the H plus will add to the double bond. Of the Br negative here as well, but it won't do anything yet. Right, again the positive charge ends up here, but also what can happen now is this double bond can resonate and put the positive charge on the end of the chain, and then the Br negative comes in, attacks that C plus, and we end up with our second product, which I will call B. Alright, so what I'm going to do is I'm going to use thermodynamics to describe why this happens, or an energy diagram that describes the thermodynamics and kinetics of this process. Alright, so here's what we're going to do. We'll draw an energy diagram, and the energy diagram will have energy on this axis and reaction pathway, or reaction coordinate if you'd like, it doesn't matter, on this axis. Now we're going to start out here, and here is where we'll see the reactants, which are the diene and HBr. Then what's going to happen is we're going to end up with two distinct energy pathways that will describe the formation of product A and product B. Alright, so this will be one of them, and this will be the other one. See if I can draw it the same way. That's better. Right, so it turns out that this is the energy curve, or the curve for product A. And A is going to be this product here. And this is going to be product B down here. Alright, so that's B. Now the reason that B is more stable than A as a product is because it's a more substituted double bond. And what I mean by that is this double bond has two carbons connected to it, while this double bond has one carbon connected to it. And the more carbons you have connected to a double bond, the more stable it is. So, more substituted double bond. So I'll say this one's a less stable because it's less substituted. Alright, well let's look at the energy diagrams themselves, and what you'll notice is that we end up with these different heights in these curves here. And what we're looking at is these little energy wells in here, and at these energy wells that's where you're going to find these carbocations. So this carbocation would be this one here, the one that leads to product A, and this carbocation will be the one that ultimately leads to product B. And you can see that there's going to be a stability difference in these particular carbocations. This carbocation is primary, so it's less stable. And this is a secondary C+, so that's going to be more stable. Alright, so what you'll see here is that the carbocation that forms product B is less stable than the carbocation that forms product A. But you can see that the product from B is more stable than the product from A. Alright, so that brings us to deciding what the kinetic and thermodynamic products are, or if you'd like, the kinetic and thermodynamic pathways. When we're talking about kinetics, what we're talking about is difference in activation energies. So here is the activation energy for product B, and this is the activation energy for product A. The activation energy is defined as being the energy it takes to get from the reactant to the top of the highest peak here, and that's what we're looking at. So these are the two activation energies we're comparing. Now, because this carbocation is less stable than this carbocation, it stands to reason that the activation energy required to get to the less stable one is greater than the activation energy required to get to the more stable one. The one with the lowest activation energy is the kinetic product, or the kinetic pathway if you like. That's got the lowest activation energy, and this will be for A. Alright, so the kinetic product is going to be A because it has the lowest activation energy. See, here's A here, and it has a lower activation energy to get to it. The thermodynamic product is the more stable product, and that's going to be B. And the reason we're saying this is the more stable product is because it has a lower energy. So just to summarize what I'm talking about, kinetic products, we're talking about activation energies, and we're always in this region of the energy diagram. And we're talking about thermodynamic products, then we're talking about the more stable product, which is over here in this area of the energy diagram. And B is the more stable product than A because it has a lower energy. Remember, this is energy on this axis, and energy is increasing, so B has a lower energy than A, which makes it more stable. And so we can see what the kinetic and thermodynamic products are here. This allows us now to explain why we get this distribution of products. So what I can tell you is this: at low temperature, what's going to happen is the reaction will struggle to get over these activation energies, and it will go pretty much for the lower of the activation energies because there's less energy available in the surroundings to allow this reaction to occur. So it'll go for the lowest activation energy. So the kinetic product will be this one because it has the lower activation energy. So that's A there. So that's A, and that's B there. Right, so A is the kinetic product, it's got the lowest activation energy, it will form at low temperature. Now, if we have enough heat available, what's going to happen is that it will be able to get over both of these, but it will prefer to go for the higher one because it produces, in the end, the more stable product. So that explains why, at higher temperature, we get most of this one formed, because we're going to use a thermodynamic pathway at high temperature, and we'll use a kinetic pathway at low temperature.